So we're going to apply our new technique, this f of c approach, to some of the familiar examples that we looked at in our other set of notes. So we need to be able to work with these two techniques interchangeably, and so that's what we're going to do here. So I've got our kind of formula statement here. The first derivative at the point C is found by applying the limit to our same difference quotient there. So we're going to do that here. So I've got f prime of c is equal to the limit as x approaches c of, and now f of x is my function that I see here, so negative 4x plus 3 minus f of c. So that means I'm just going to plug c into this function, and so that's going to be negative 4c plus 3. But then my denominator is always going to be the same thing, because the 2 points that I'm dealing with are the point c f of c and some other point on the curve x f of x. So we're always going to have this x minus c in the denominator. Now if we'll recall, last time we said that, all right, we have a linear function in this case, so no matter where along the graph we are, our slope should be negative 4. So that means our first derivative formula should be negative 4, independent of the value of x previously or the value of c now. So that should be what we end up with when we're all done. So I'm going to continue forward here. Can't take my limit yet because I'll end up with 0 in the denominator. So I've got a clean house in the numerator. So I've got, if I do a little change work here, make that plus, distribute this negative, so this becomes plus and this becomes minus. So what we've got in the numerator is negative 4x plus 3 plus 4c and then minus 3. And then still x minus c on the bottom. So we can see hopefully that the 3's are going to cancel each other out. So we end up left with a limit as x approaches c. Haven't removed that discontinuity yet, so we've got to keep going. So I've got negative 4x plus 4c over x minus c. So as we did in the last one, we've got to figure out some way to be able to cancel out that x minus c on the bottom. And so if we look at the numerator, hopefully we can see, excuse the pun there, that we can undistribute a 4, or a negative 4, pardon me. And so if I do that, I end up with x minus c left behind inside the parentheses. I've got x minus c in the denominator. And so now we can reduce the x minus c's away. So we get to a point where we have the limit as x approaches c of just negative 4. So now we no longer result in that indeterminate form by applying our limit. In this case, we have no place to plug in c in place of x to turn the x's into c's, but that doesn't matter because we expected this. We knew that our formula for the first derivative along the slope of the line anywhere along this linear function, independent of where we are, is going to be negative 4. So here's another function that we already found the formula for the derivative. So you can take a look to our notes to see what that formula was. But we're going to find it using this new technique, the f of c approach. So we've got f prime of x, the first derivative, is equal to the limit as x approaches c of. So again, first thing is f of x. So I'm just going to copy down the function as we see it, x squared minus 4x minus 12. And then we're going to subtract f of c. So that means I'm just going to plug c into my function. So we get c squared minus 4c minus 12. And then in the bottom, as always, x minus c. So I'm going to continue forward here. My limit as x approaches c of, now I've got a couple things that I'm going to do here. I'm going to distribute the negative to everything, and I'm going to group together my like exponent pieces. So I'm going to group together the x squared and the c squared. So I'm going to have x squared minus c squared as my first couple of terms. Then I'm going to group together the non-squared terms. So negative 4x and minus 4c. So I've got those two grouped together. And then hopefully we can see that the 12s, I've got a negative 12 here from the first set of parentheses. When I distribute the negative, this becomes a positive 12. So those are going to cancel each other out. So this is all that I have left in the numerator. And then I have this x minus c in the denominator. So somehow I've got to cross cancel away the x minus c from the denominator. I have to remove that discontinuity so that we can then apply our limit. So I've got my limit as x approaches c. And so the technique that we're going to use is we're going to factor this part of the expression, and then we're going to factor this part of the expression. And so we've already factored x squared minus c squared before. We know that that factors into x plus c times x minus c. So we've got that much. And then from the second part, also similar to something that we've done before, and I'm sorry, this should be a plus c right here since we distributed a negative. My apologies there. So I'm going to undistribute a negative 4 from this second half of the numerator, and when I take out that negative 4, we're going to end up with x minus c as well. I still have this x minus c in the denominator, and so hopefully we can see that we're indeed going to be able to remove our discontinuity. So just like we did in the other technique with the h's everywhere, we could cross cancel those away. So too here, I've got x minus c in the denominator, so I can cancel out the x minus c from the first part of the numerator. I can cancel out the x minus c from the second part of the numerator. I have to be able to reduce it everywhere, just like with the h's. And so what does that leave us with? We've got the limit as x approaches c of x plus c is what we have left out of the first part of the numerator, and then minus 4. And so at this point now, we don't have the x minus c in the denominator. We've removed the discontinuity. I can apply my limit. I can set the x's equal to c's. And so we end up with our first derivative is c plus c minus 4, or if we clean that up, it's 2c minus 4, which again is the same formula. It was just 2x minus 4 using the other technique. It's the same formula for that first derivative.